All right, so again, looking quickly at Unit 4, what was supposed to be covered this weekend. Obviously, Unit 4 is dealing with statistical analysis here. Okay, it's dealing with statistical analysis. And we started off with looking at graphical analysis of data. Okay, so basically, what are the different graphs that are used to display data, right? What are the main ones? What are their parts? What do they do? What do they show? And then after we looked at the graphical stuff, we looked at numerical analysis. All right, so looking at numbers, right? Numerical meaning numbers, right? Looking at the numbers of them, and looking at the different things that we can do to look at the data, right? So taking the average versus taking the median, right? Looking at the mode versus your mean, all of that kind of stuff, and really diving into those. Okay, and hopefully you noticed here they're pretty big sections, which is why you have multiple quizzes here. All right, so there's always, of course, natural breaks, so you can go through and break it up as you want. All right, but those are the 2 units that we covered this weekend, along with finishing up Unit 8 there, or sorry, Unit 3. All right. So now we're going to start, and kind of my goal for us today, obviously in class, is to still cover our 3 lectures here. All right, so we've got 4.3, 4.4, and 4.5, but I have a really, really strong feeling that we're only going to get to cover 2 today. So if we only cover 2, that'll be fine. Okay, let's get started here. All right, so first off, 4.3, we're looking at gathering data in the inferential statistics. Okay, so let's look at our overview here. All right, so when we're talking about our data here, okay, obviously data collection means, you've got to go out and you've got to get the data from somewhere, right? Numbers have to come from somewhere, or, like opinions. And the example that they're giving here is voting for a president here. All right, but you may or may not know this, right? You may or may not know this, but there's actually an electoral college, right? So even though every single person votes, right, they don't count every single individual vote when they're making up who's going to win the president here. Okay, what they do is and this one's talking here about predictions. Okay, so when it leads up to the voting, okay, what they'll do is they'll gather an amount of data from looking at different factors, right? But what they'll do is they'll take a sample of the U.S. population and say, okay, right now, who are you voting for, this person or this person? And that's how they can get to see who's kind of leading the race here. It's not an exact science, which is why you can still have upsets. But what they do is, again, they take a random sampling, and they ask, rather than asking every single voter, because it would take so long. Right? And that's why maybe you've heard the phrase, oh, this person's up in the polls. Well, yes, you're up in the polls, meaning the random amount of people that we sampled, you are winning, right? So that's kind of a good predictor there. Okay, and since the researchers in this little fake example here use a small data set and make a prediction based on it, okay, their predictions are what's called that inferential statistics, right? They're extending beyond what they actually know to make what's called an inference, right? An educated guess. Okay, so again, of course, the government has been asked to review an advertisement for a weight loss program. Okay, the company promoting the program claims the program user can lose an average of 20 pounds. Meanwhile, a rival weight loss company has done its own studies on this program. It's found that a sample of 25 users lost an average of only 17 pounds. Okay. So the question becomes, obviously, is this an effective weight loss program? Okay, and you could click yes or no, right? And it's going to come down to, okay, well, do you think that it's effective because they lost weight in general? Do you think it's effective because they lost 17 pounds? Or is it not effective because they lied and said that you should lose 20 versus 17? Okay. So a lot of that then, of course, comes down to our favorite kind of data, public opinion, right? It always comes down to public opinion. And that's why there are some things, right, like obviously public opinion, like we said, but like with the who are you voting for, right? Maybe that's flip-flopping every day versus something like if I asked you how tall are you, right? If I asked you how tall are you versus how do you feel about whatever, right? So your opinion on something might change a little bit more drastically than your height, right? And we'll talk more about that in later units here, right? The impact of public opinion here. All right. But again, looking at inferential statistics here, okay? So we were able to divide earlier into inferential and descriptive statistics, okay? And basically, if we look really quickly here, descriptive statistics uses graphs and numerical analysis to describe data that has already been collected. Okay, that's the key there. It's already been collected. Okay, we're looking at numbers 1 through 10. We're going to make a decision or a description based on numbers 1 through 10. All right, when we're looking at inferential statistics, okay, it's where we use sample data to make a prediction about a larger population. So this would be like saying, okay, out of 100 people, or to figure out what all 100 people are saying, we're going to take a random sampling of 10, right? So it might actually be person 2, person 25, person 32, right? But I'm going to make an educated guess here, right? A prediction based off of my random sampling, okay? And there's 3 phases when we do inferential statistics. All right, you have phase 1, which is gathering the data here. Okay, you have phase 2, which is organizing and analyzing your data. And then you have phase 3, which is probability-based inference. Okay, probability-based inference. Again, what's the chance that this is going to happen? Right? What is the chance that it's going to happen? And of course, obviously, these first 2 stages are also there for descriptive statistics. This last stage here is what's added on for inferential statistics, right? Going beyond what we already definitely know based on our data and making that prediction. Okay, so if we take a deeper look here at the different phases, looking at phase 1, it is collecting data, all right? And I know that you guys know a lot more ways than just this, okay? But there's, surveys, there's counting, there's computer programs, questionnaires, Google Forms, right? Anything that you can think of. I don't know if you've ever seen it, like someone walking on the street saying, hey, can you answer a few questions for me, right? All of that kind of stuff, okay? But the most important thing with collecting data is that it has to be done well and it has to be done reliably. Meaning you can't fake data, right? You've got to make sure that you've collected a random sampling, right? You've got to make sure things like that. Like for example here, if we wanted to have a new phone, right? And you wanted to know how young students felt about this phone. Okay, you can't get your sample, like you can't ask people about the phone that are, I don't know, 45 and above, right? You can't ask a lot of adults about how they think their kid feels about the phone, right? It doesn't make sense. Ask the kid themselves. Otherwise, you're not going to have reliable data there. Okay, so this leads us to our ways to collect data. Okay, so there's 3 primary ways. Obviously, there's a lot more, but there's 3 that we're going to really talk about: observational studies, surveys, and experiments. Okay, So observational studies, if we give the definition, it's studies that collect and analyze data without changing existing conditions, right? So you don't go in, you don't impose anything. And right here's a really good description of an observational study, okay? And it's just collecting data by observing occurrences, right? So a couple examples, they said number of people who do not wear seatbelts, right? They don't change anything, they don't ask anything, they just watch people as they drive by in their cars. Or blood pressure readings for a group of elderly people, right? So maybe they go into their normal doctor and they get their blood pressure readings, right? Something like that, okay? Then surveys, okay? Surveys usually involve asking people questions, right? Again, can I stop you? Can I ask you to take a survey for me? Or can I give you a Google form, right? Those are types of surveys, okay? And obviously for a survey to be accurate, the responses must be honest, okay? But this raises a problem here because sometimes people aren't honest. Like for example, of course, if you ask someone if they wear their seatbelt, they're gonna say yes most of the time, right? So a lot of times with surveys, if it's a question of morality there, people might be more inclined to be dishonest, right? Or if it's something that, you know, is technically against the law, like wearing your seatbelt, you have to wear your seatbelt, it's part of the law. But on a survey, they might get different data than if they looked at it as an observational study, okay? And then finally, the last one is an experiment here. And I know that you guys know a lot about this. And basically, you've got your treatment group and your control group, right? You've got your treatment group and your control group, right? And this is talking about changing our dependent variable, right? So the one that I think of is always with people taking new drugs, right? They'll give everybody a pill and they won't tell which people have the drug and which one's the placebo, right? The sugar pill. All right. But of course, we compare our data from the treatment to the control group and really taking a look at that. Okay. Oh my gosh, perfect. So right there, a perfect example of that is drug trials when they're looking at the effectiveness of new medicines. All right. Of course. Okay. So then looking at phase 2, which is our data organization and analysis here. All right. So of course, once you've collected all your data, you actually have to organize it into something that you can read and condense. And obviously in the earlier study, we talked about a lot about how once you've organized the data, you can look at graphically manipulating that data set. All right. But basically, again, taking the data and displaying them visually, analyzing is calculating some form of statistics, right? So your average, your mean, your median, your mode, right? Something along those lines. Maybe your standard deviation, right? All of those things that we worked on in 4.2. All right. So again, an example of this would be like a histogram. Histogram is data analysis, right? Data organization, right? It makes a really pretty table, right? It shows us a graph. Same thing, tables would be a organization, pie charts, graphs, right? But something that's going to be data analysis is finding that range, finding that mean, that standard deviation, that max value, right? So again, the difference really being here, the data organization is making it visually, and data analysis is being able to calculate it and get a value out. All right. And then finally, phase 3 here is this probability-based inference, okay? So now that we've gathered our data, looked at it, made some analysis here, we can then move on and basically make a prediction where we can predict what we think is going to happen. All right, and they use the word inference here. Right, so if you don't know what the definition of inference, it's a conclusion drawn by using sample data to make predictions about a larger population. All right, so when we draw conclusions or we infer something, it's based on probability, and that is the chance or the likelihood that it's going to happen. All right. So if we look here, all right, for each of the events listed below, we're going to find the probability of attaining the exact result and determine which will most likely indicate an unfair coin or loaded dice in the deck of cards. Okay. So event 1 is the 5 dice are rolled and each one shows a 6. All right. The next one is 5 coins are tossed. All of them come heads up. And event 5 is a card is drawn from the standard deck, then replace the card, or the deck is shuffled. This is repeated 4 more times for 5 cards, and they're all aces. Right? So it's looking at our probability. So the probability of us rolling a 1 a 6 is 1 in 6 because there's 6 sides to a dice. All right. Flipping a coin, it's going to land on heads 1 out of 2 times because there's only 2 sides to the coin. All right. And then with a deck of cards, you've got 52 cards. All right. And 4 of them are aces. So we've got a 4 out of 52 chance. All right. But that's every time you do something, right? So every time you roll a dice, you have a 1 out of 6 chance of getting it to land on a 6. All right, you've got a 1 in 6 chance for it to land on the 6. All right, so every time you roll that dice, you have a new probability, and it's at 1 out of 6. So you can see here, every time we roll the dice, all 5 times, it represents a 1 out of 6 chance that you're going to land on the value of 6. All right, so we multiply those together and we can see that the probability of this happening is 1 out of 7,700. Okay, with our coin here, right? Again, we only have 2 sides, so we have a 50% chance it's going to land on heads, right? But again, every time you flip the coin, it resets that 50%. All right, but this one here is a 1 in 32, right? So this is a much, much greater chance than something like this. Okay, and if we look here, of course, again, our deck of cards, so we have a 1 in 13 chance of pulling an ace. All right, because there's 4 aces in a deck of 54 cards. All right, but every time we pull a card and we reshuffle and we put them all back, again, we have that 1 in 13th chance. Right, and clearly you can see that the probability or the chance that this is going to happen is our 1 in 300,000. All right, our 1 in 300,000. So if we were looking at this and had to make a conclusion, right, which one's least likely going to happen, obviously it's going to be the 5 aces on 5 cards here. All right, it's going to be the 5 aces on 5 cards here because look at it's saying you have a 1 in 370,000 chance of doing this. All right, so this most likely is indicating a deck of cards that's loaded, right? So a cheating deck of cards. Okay, and yes, I know we're talking about cards and dices here. There's that game where you count cards, or that movie that counts cards, right? So that's how sometimes they can find cheaters in hotels, right? Same thing like that. If you continuously roll and it's an unlikely amount, right? It kind of raises some red flags. Or if they're always getting, 21 in blackjack, right? That raises some things here. And so again, statistics can be really, really helpful in that scenario, but obviously they can be helpful in a lot more situations here. Okay. On the previous page, okay, of course, we probably didn't need to do calculations, but we can always do them for later things here, okay? But this is saying here, if your friend drew 5 aces, like if you were playing, I don't know, like War or something, like a card game, if you drew 5 aces, you would kind of look strongly and be like, how did you do that, right? And then obviously you would want to look and see if it happens with a second person, right? Looking at a different number of samples, right? So looking at 2 people versus just 1 person, okay? Because Two people each drawing 5 aces is approaching what we call statistically impossible, right? It's really, really, really limited chance that it would happen, okay? So it is like statistically impossible, right? You may have heard that in a movie somewhere, or maybe a teacher, or you know, your parents, but saying it's statistically impossible, which means it is very, very, very unlikely. Okay. And so what about something that might be not as obvious? Okay, not as obvious. So for here, they said you have a neighbor that makes only about 50% of his free throws. If he told you yesterday that he made 10 consecutive free throws, that's 10 in a row, would you believe him? Okay. So which of the following are good reasons to believe your neighbor's claim? All right. Well, one, your estimated average of 50% may be inaccurate. Okay. You don't know how many free throws he shot to get this result. He's known for his honesty. While it's unlikely, it's not impossible. He looked you straight in the eye the whole time he was telling you about it. Okay. So depending on who you are, you might choose different things here, right? So you might be someone who's saying, oh, well, he's always been honest with me, and you looked me straight in the eye. And if I click on all of these here, it's going to tell me that nope, that's not correct, right? So okay, maybe we take out the more personal things, like okay, he's known for his honesty, but maybe he's embellishing a little bit here, or he looked me straight in the eye, but that doesn't mean he was telling me the truth. Still not correct here. Okay, so then we got to look at, okay, well, it's unlikely, it's not impossible. Okay, so it could happen. But do you really think that your estimation was incorrect? Maybe you don't know how many free throws he got there, right? Or again, it's unlikely but not impossible. All right, and so let's take a look at what the actual answers are and how do we know them. All right, so again, it becomes like the coin problem here. All right, you're either going to make the shot or you're not going to make the shot. And we couldn't say that our estimate of 50% was incorrect, because we're going to believe ourselves on this one, that we know he makes about 50% of the shots here. All right, so we're going to believe ourselves on this one here. Okay. And so since it's similar to the coin flipping problem, okay, what we know is we're going to take that 1/2 and we're going to multiply it 10 times, right? Or saying 0.5 to the 10 power. Okay, or again, 1/2 to the 10th power. Okay, again, the reason being, he's got a 50% chance of making every free throw, because that's what we've concluded he's likely to do. Okay, so when we do the probability here, it's about 1/10 of 1%, or 1 over about 1,000, that he's going to make 10 basketball shots in a row, or 10 free throws in a row. Okay. So it's looking like it's not very likely here. Okay. Then another one, if you have it, right, you could run a simulation. Okay, you could run a simulation and do a random number generator and assign possible outcomes. Okay, so basically they're saying 0 through 4 represents baskets, while 5 through 9 represents misses. All right, and then they'll put them and let it go out and look and see, okay, how many successful attempts did he have? And if you look here, there's only, I believe, one chance where all of the numbers are successful attempts here. Okay. So in the simulation, what's the highest number of shots in a row? It was 5, right? It was 5 right here. All right, so they're arranged in groups of 5. Okay, Now, of course, an advantage of a simulation, if you have the ability to do one or to make one, is that it gives you a good sense of what's likely to happen. Okay, and of course, the answer on the other page, okay, the answer from the other page was an 8. All right, you could have also gotten this answer of 7. And what they're saying here is in the second to last row, there are clearly 7 baskets. So the second to last row, there are 7 baskets, starting with 0. All right, and I didn't fully understand this one either. And so what I would say here is that this is not a good way for them representing their data, right? This is not a good way for them representing their data. And so this is what we talk about is you have to make sure that your data is easily understood by somebody who's trying to read it, right? So if we look at this data and we can't figure out what they're asking us, right? If we can't figure out what they're asking us, then it's really difficult to read this data here, okay? Because what apparently they were saying is, in the last slide, was that they wanted to arrange their data by sets of 5, okay? So they arranged their data in sets of 5. But now when it's looking, it wants us to look at, like it wants us to look at to see where the longest string of yellows is, right? And technically, okay, what they're saying is it 7 because we go 1, 2, 3, 4, 5, 6, 7, right? It goes 6, 7. So that would be the 7 in a row there. All right. And that's where, again, I don't think they did a very good job of labeling this maybe, or putting it in order. And then of course you're going to come up with this when we get back to looking at data and collecting our own data. Again, moving forward in your math classes, moving forward in your science classes, but of course, obviously outside of that, right, you can use this for a lot of things, but you've got to be able to make sure that your data is readable and your audience gets what you're trying to say there. Okay, so if you didn't understand what they meant by getting all of these in a row, they're talking about this 7 right here. Okay, they're talking apparently about this 7 right here. So they're saying they ran a random number generator, and I guess what they're saying is that they ran it like this. They ran it like this. Okay, but each of those are broken up into columns of 5, right? So again, labeling your data and showing your data in the best possible way is key here. All right. And getting back to the simulation away from the data, right? So simulations can be very, very advantageous because it can show many variables, right? And a lot of people will use this, they'll use a simulation to run, again, quote, run their product through a lot of different scenarios here, right? So instead of actually having to go out and shoot this many basketballs, they can run a simulation that will do it for them. All right. You can also see people use simulations for a lot of different products, like let's say cars, right? Sometimes they'll use cars or simulations for cars if they're car crashing, right? What happens if in a car crash? Is this car going to be safe? Or looking at airplane parts, right? So simulating how would that fly? How would this affect something like, I don't know, wind resistance? Okay, so you can make simulations, and what they'll do is, again, they'll be able to run through a lot of different scenarios to give us a better probability of things. Oh, and then another one they said is weather prediction, right? So looking at weather predictions, that's one you're most familiar with, is if you look on your weather app on your iPhone, right? Sometimes you can look at the radar, and what they'll do is they'll have where the clouds are now, and then they'll use a simulation to show you where they think the clouds are moving, right? They'll use it to show you where they think the clouds are moving or where the storm's headed, right? It's not an exact science, but it's a good guess, okay? So then they take a step back here and talk about how to set up a simulation, okay? And of course, if a simulation is set up correctly, right, takes everything into account, it becomes actual results and not just probabilities, okay? So, for example, if you flip a coin repeatedly, you expect to get on average an even number of heads and tails, right? Because it's a 50% chance it'll land on heads and a 50% chance it'll land on tails, all right? But a simulation might have 20 flips, out of 20 flips might have 15 heads, 15 tails, all right? So when we're looking at a simulation here, we have a couple steps to obviously set it up. So one is to describe the possible outcomes, all right? 2 is to assign one or more random numbers to each outcome. 3 is to choose a source of random numbers. 4 is to choose a random number. 5 is is based on the random number, right? We're going to note the simulated outcome, right? Because every number is associated with an outcome. And then we repeat 4 and 5 multiple times. Choose a random number, write down the simulated outcome. Choose a random number, write down the outcome, okay? Until it shows a stable pattern, okay? Until it shows a stable pattern, right? So for example, with this 15 and 5 here, all right, you might flip it, and again, you describe the possible outcomes. You think it should be about 50% here. Right? It's either going to be heads or tails, okay? Then of course, after you state the possible outcomes, all right, we said random numbers, right? You could have 1 be heads, 2 be tails, or you could do it like the basketball and assign multiple numbers, right? But regardless, you have the numbers assigned to different outcomes, all right? And then you look at those random numbers, right? So you can have what's called a random number generator, all right? And it'll generate numbers, and then you choose that random number, write down the outcome, right? So if you said 1 is heads, everywhere you see a 1, you write down heads. Everywhere you see a 0, you write down tails. Okay, and you repeat that again until there's a stable pattern. So if we do it for this first 20 here, obviously it looks like there's 15 more, there's 15 heads while there's only 5 tails. All right, so this doesn't look like the pattern that we expected, right? It doesn't mean it's wrong, but it doesn't look like the pattern we expected. So maybe we'd flip a couple more and see if the pattern that is emerging here is going to be more consistent, right? That's, again, of course, we're going to get to a stable pattern there. And then obviously step 7 there is to analyze our results and report our outcome, right? So look at our data, analyze our data, and then display it. All right, and perfect. I just mentioned this, so our random number generator, okay? So we can generate random numbers, and the whole point is when we assign those random numbers, we want to show flipping like fair things that aren't skewed to one side, they're not weighted or anything like that, all right? So the same thing happens for our random numbers, right? So when we're looking at random numbers, if you were to ask a friend, right, give me a number between 1 and 10. If you ask them that a lot of times, right, usually people have a favorite number, right? So you might be more inclined to say your favorite number, or you might say all odd numbers, right? Some form of pattern that you don't realize you're doing. But then that makes the numbers that you are randomly generated, they're not so random anymore. They're biased, right? So we need a lot of random numbers, and the 2 ways that we can really get them is, 1, this thing called a random number generator. Okay, it may be found on a graphing calculator or computer. Depending on your level of graphing calculator, you have one of them. Okay, or you can have a random number table, which is simply a list of random numbers. All right, so if we click here,
Calculators and computers both have random number generators. When would it make sense to use a number generator instead of flipping a coin or spinning a spinner? Answer: whenever you need a large number of trials done, it is faster to use the random number generator on an electronic device.
yep, perfect. Because this is something that we could do. We could spin it on a spinner here, but think about it. Every time you spin it, it's going to take you, 5 or 10 seconds, depending on how fast it slows down. Okay. And then if we look here at our random number table, okay, so this is an example of a random number table. Okay, and obviously you can see that the numbers here go from 0 to 9. All right, so you would have to assign values for numbers 0 through 9. Okay, and how you read this depends on you. You can go down, you can go across, you can go down 5, over, right, whatever. But this is an example of a random number generator. Or sorry, a random number table. All right. With a random number generator, it's a device. So hopefully they show us a good example here. There you go. All right. So generate random numbers. Beautiful. It generated them. We generate new random numbers. And it will keep doing that and filling in random numbers. Again, this one here, again, is set for 0 to 9. All right, but there are a lot of different random number generators. Okay, they could be from 0 to 100. They could be from 0 to 5, right? It all just depends on the parameters that are set here. Okay, but that's an example of a random number generator. Okay, then when we look at here, there's 2 important things to remember about the random number generator and random number tables. Okay, even though the numbers are typically arranged in 5-digit groups, these groups are not significant. Okay, so again, both of those that we just looked at had them grouped in 5s, but if that doesn't make sense for you, it doesn't have to. All right, people just normally pair things in 5s because it's easier to count up, right? I know a lot of us know our multiples of 5s better than we know, maybe our multiples of 4. Okay. And then there's no pattern to the numbers. That's another key important thing. All right. In a set of randomly generated numbers, there should be no pattern. You shouldn't be able to predict the number that's coming next. Okay. So if we look and see how the numbers can be rearranged, okay, these are rearranged in groups of 5s. If we rearrange it in groups of 2, and 3, 4, 10, whatever. Okay. So it truly doesn't matter how it's grouped together. It's whatever fits your needs here. All right. And so again, created this list of 10 5-digit random numbers. All right. And for this one here, when we group them in 3s, notice that since we didn't change the total number of digits here, all right, and if 50 digits, we have 2 left over. All right, so it would we have 2 left over. All right, if we totally needed another digit here because we were specific about our groups of 3, then that's fine. You would just have more than 50. All right, and same thing here. If we group it by 4s, obviously we have 2 left over, so we'd have to fill those. Okay. So then moving forward here, assigning random numbers to events here. Most standard random number tables use the digits 0 to 9, like we mentioned, okay? And when it's possible to program a computer to produce the numbers 1 through 6, okay? Or up to 1 to 24. All right, in our basketball problem, the success rate was 50%. So we assigned half of the numbers 0 to 4 to mean success, and the other half 5 to 9 to represent missed shots. If you don't need all 10 digits, one strategy is to state ahead of time that the numbers will be ignored. All right, so you can either, if you have the ability, you can limit the numbers that are used, Or you can make that statement in the front that, hey, if it hits these numbers, we're just gonna ignore it here. All right. Same thing with the other values. So we can decide to ignore values if we are using a random number generator or a random number table, and we don't have the ability of shortening it. So again, of course, if we're looking at a dice, right, and we want to assign each number just the side of the dice, we don't need numbers above 6, obviously, because there's only 6 sides to a dice. So we could just say, all right, ignore any of these other numbers, okay? If we are looking at a simulation with percentages, right, so looking at percentages of our outcomes, that would be something maybe like the number of hits of a baseball player. Okay, we can assign 3-digit numbers to be hits, right? So we could look at things larger than between 0 and 10 here. Okay, so we could look at 000 to 256. All right, and then 257 to 99 to be outs, assuming, of course, that our player's batting average is this 257. Okay, so again, if they had a higher batting percentage, we would make this value of hits higher. Okay, and so this can be really, really useful. And again, it's knowing what do you have, what do you need, and kind of what's at your disposal here. All right. So then here, these are some quick questions that you guys can go over. But looking at your calendar for the first semester, you notice that your teacher gives a pop quiz 75% of all Mondays. All right. So you can try to set up a simulation to predict pop quizzes for the semester, right? And you can actually do and look at that. So of course, this is going to walk you through what's the best and simplest first step here. Okay, so I'll let you guys walk through those for the sake of time here. And then same thing with this newspaper survey. Okay, so the first one was looking at where you already have a prediction, right? And this one's now looking at survey in a newspaper here. All right, and something I want to point out is that you will need to probably, most likely, right, need to generate some random numbers here. All right, so you can just hit that random number generator. Okay. So then in the newspaper survey question, okay, you're going to notice that you have a single set of data, and that single set of data doesn't always represent the truth about a population, okay? So one simulation or survey might generate an outcome that is significantly different than the actual probability, all right? And there's many reasons as to why this can be true here. But again, like I mentioned earlier, if you asked people how they felt about a new cell phone, right? If you only took the opinions of people at St. Lawrence, right, peers about the same age, right, it might not be how everybody feels because you're one specific class of individuals, right? You would be high school students. But what about middle school students if they have cell phones? What about your parents, your grandparents, right? So you have to take those things into consideration, and that's how sometimes a simulation or a survey might not represent the total outcome. Even if like you get a strong indication that 95% of students at St. Lawrence love this new cell phone, right? The entire population might be more like 50-50 because you only looked at one specific group of people, okay? So again, that's why it's going to be really important to perform many simulations or to use a larger sample size for the survey, right? So to break out of just that small little group that you might have asked, right? And this is kind of a law here. So it's called the law of large numbers. And what it does is it says that, hey, if you get more people to answer these questions, it's going to be closer to what your theory predicts. Okay, your estimates are going to be closer to what you think, right? So, law of large numbers, if we look at this here, if we roll a dice 6 times, you might get a 1, 1 4, 2 4s, or no 4s. All right, there's no rule that says you have to get exactly 1 4 when you roll the dice 6 times. It's not like you get a 4 2 1 5. It's not like you get all of them. right? So you can get a different combination of 4s there. All right. But again, if you roll the dice 60 times, you can expect a 4 to come up 1 over 60 times. That's because each time the dice is rolled, again, there's a probability of 1 over 6 that the result will be a 4. All right. So if we roll it 60 times and we get 10 4s, that's really, really close. Okay. Same thing, if we get like a 9 or 11, that's really close to the 10 that it should be based on our probability. Okay. And as our sample size gets larger, our values that we get closer to our calculated probability. All right, so a reason about this is if we roll the dice 60 times and we get 12 4s instead of our 10, okay, it's reasonable, right? It's close to our value. It's not something insane, all right? So we can be reasonable with that, all right? And for this one, if we were to step it up to 120, right, roll it double the amount, we would get closer to our actual value here, right? So we'd get closer to our actual value that we were looking for. But if in the same 60 dice, we get 22 4s, okay? We can conclude a couple things here, but the major one is that maybe there's something wrong with our experiment. Right? If we think that it's not the number of times that we rolled the dice, we might want to look, is there something that went wrong with the experiment or something that's out of the ordinary? Okay, so then we looked at that weight loss problem in the beginning, right? So 20 pounds versus actually losing 17, okay? If we look at this here, okay, we can say this company agreed to follow the industry standard for analyzing data given below, which is when the probability of a result is less than 5%, the result is unlikely or a fluke. Okay, in this case, a claim based on that result is misleading. All right, so what they're saying is as a standard, the weight loss industry, in this example here, came up with a set guideline, which is if it's less than 5% chance of happening, that is not likely to happen. It's what's called a fluke, right? And you can't report it as the truth. That's misleading. All right. So maybe there was a couple people who lost 20 pounds, right? But it was not the majority of people. So you can't report that out as true. All right. So then here, look, if we look at using the method, they found that if the true weight loss is 20 pounds, there's a 0.7% probability of getting 17 pounds. All right. So again, conclusion 1, the probability of the sample result of 17 pounds lost is unusually low, but not outside of the industry standard. It is possible that the people who were selected didn't lose as much weight as other people in the program, right? So this is one conclusion, okay? Or the other conclusion could be a sample result of an average weight loss of 17 pounds is too far from the claim of 17 pounds. Okay, or sorry, of 20 pounds. It is likely to be more representative of a larger population of program users, which means that the weight loss company should be considered misleading. All right, so that's the question you got to ask yourself here. If the true average weight loss is 20 pounds, then there's a 0.07 probability of getting 17 pounds. Okay, so is 17 pounds really far outside the norm? Well, 7% is greater than 5%. All right, so since 7% was greater than the 5%, right, our first answer is true, okay, because it's not very likely, but there's still a chance that it could happen. It's not under that 5%. Okay, again, statistical analysis allows for probabilities as low as 5%, but no lower. Okay, 5%, but no lower. And again, since 7% was larger than the 5, it had to conclude that it wasn't misleading. It wasn't misleading. Okay, so looking at these, of course, I'll let you confirm and look through and check your data here. I just want to make sure for the sake of time, we can get to the next one here. But take a minute or two and really try to digest this. I know I flew through this one here. We had that issue in the middle, but again, really try to make sure you go through this and read it, because I know it can get a little bit tricky when we start talking about numbers, right? When we actually start talking about numbers. All right, but basically, if we look here, again, our inferential statistics is making an inference, right? We're making an educated guess outside of our data that we've collected, right? So the three phases in order to do this is to collect our data, right? So data gathering, then we have data organization analysis, and then we have probability-based inference, right? So making that guess there, okay? Ooh, splash, sorry. All right, so then, again, looking at our experimental, our theoretical, and then comparing, all right? So when we did this, we talked a lot about the different steps in each of these phases here, all right? And how do we gather our data? Are we gonna do it experimentally, through a survey, through whatever, right? With our data organization and analysis, how are we going to organize the data and represent it so that it shows us something good, right? In a way that's easy for people to understand. Is it labeled? Is it the most appropriate graph for that data set? And then finally, of course, the probability-based inference, right? We talked a lot about it. Has to be, representative of a larger sample set, and it has to kind of follow the trend. And we just learned about that the general rule is above a 5% here. Okay, so of course with this one, of course, we only have one quiz, so that's something that you guys can work on tonight when you look over it. And then we'll try to get through as much of this as possible. We'll just get to these two lessons here today. And for random variables, okay, so we're going to start with that guy. And for this unit here, we have 2 quizzes and 1 extra credit opportunity. So you'll hopefully take a look at those tonight. All right, but let's get started on this one here. So looking at random variables, okay, so we've of course talked about different sets of data, all right, and we've talked about in science, we've talked about assigning independent and dependent variables. Now we're going to talk about this thing called the random variable. And if you look at the formal definition here, it's a variable whose numerical outcome of a random event, right? So basically, it's something that it's a random number that comes up, and you're like, where did that come from, right? It makes you ask, where did that come from? Okay, so looking at our data, there's 2 types. So there's continuous and there's discrete, all right? So continuous is often written as decimal fractions, right? So they use something like weight here. Okay, you can weigh somewhere anywhere between 124 and 125. You might weigh, 124.5. Or height is another example of a continuous data. All right, versus something like discrete data. All right, so discrete data is discrete data is something where it's basically whole numbers most of the time, right? So like today's the 18th, or sorry, today's the 20th, but in here it says it's the 18th, right? 19th, 20th. Or we were talking about, like, how many school buses do you need to fit all the kids, right? There's no half school buses. So 1 school bus, 2 school bus, things like that. All right, and I'll let you try this out here, looking at discrete versus continuous, but basically number of classes you take at school, that's going to be discrete, right? You're going to take whole classes, but the weight of a bag of apples, there, come on. All right, sorry, there we go. there we go. Apologies. All right. So 2 continuous things would be like time to run a race, and then the weight of a bag of apples, right? So I'll let you go through the rest of these here, but those are just a couple more examples of discrete versus continuous. All right. And so looking at how do we actually show them graphically, okay? So looking versus discrete. So an example of showing that might be a histogram here, okay? Because each event is represented by a bar, right? Or each bar represents a class here, right? So a specific set of numbers, all right? But the key to a good histogram is to choose the right number of classes. All right, so increasing the number of classes can show clear gaps, as some histograms will appear skewed in one direction when there's too many, right? So for example, if you look at the data here, okay, it's the same exact data, all right, it's just got a different number of classes. So right here in the top one, we go 120 to 150, 150 to 180, right? So each one of these bars represents about a 30 point little range, okay, a 30-point range here. So if you look at this, it looks like everybody's, or a lot of people are in between the 150 to 210, all right? And that's kind of a very broad thing. And if we look at 12 classes here, right, you can see there are a lot more classes, there's a lot more bars, right? And there's some gaps here where people don't even fill that in. All right, so again, depending on what you want to say about your data or what you want your data to show, either of these could be good ways of showing the data. Okay, and then obviously going to continuous data, okay? So continuous data makes it a little bit more difficult to build a histogram because the classes would have to be very small, right? If we had to go into actual half units, all right? So, of course, we can still build a histogram using our continuous data. We would just have to make our classes number ranges, right? It'd have to make our classes number ranges, all right? And if we look here at our click and drag, okay, and this is what it looks like if we have our histogram with small number of classes. And you can see here, as we get to larger and larger number of classes, this graph starts to smooth itself out here until eventually, if you notice, it looks like this really smooth plot, right? It looks like a smooth graph there, all right? Okay, so this can generate a thing called a density curve. All right, so when we go from having that histogram with the very large number of classes, right, so those really tiny bars, okay, to that smooth curve right at the end that I was showing you, we call it a density curve, okay? So we call it a density curve, all right? And the formal definition of that is a curve that represents a continuous data, and what we say is the total area under the curve is a value of 1. Or 100%, okay? So the total area under our curve is equal to 1. All right, so if we look here at some characteristics here, the percentage of the values between any 2 points is the area underneath that curve, right? So looking at this, right, we would look at our area under the curve, and that's gonna give us our percentage of that happening, right? This entire area is equal to 1. And it always is above our horizontal or our x-axis, right? It's always going to be in that positive direction because we need it to add up to make 100%. All right. So looking at a couple examples here. All right. It's not letting me, so apologies. There we go. Okay. So again, density curves equal 100% or will add up to 1 on the frequency, but the density curves can have a lot of different shapes. Okay, they can have a lot of different shapes. So here's a couple examples. We've got one where it looks like this guy here. All right, we got, perfect. All right, then we can have another one that looks like this. All right, both of these are density curves. Okay, both of these are density curves and they both show different things here. All right, they both show different things. And you can go through the calculation to figure out the A values for both of those. But what this is really showing you here is looking at different sections of it and figuring out the calculation for different sections. And what this is saying here is if I look at this guy here, since this area under the curve is 0.5, I've got a 50% chance of it falling here, right? I've got a 50% of it falling there. All right, and again, of course, you can read this on your own here. It does a really nice job of explaining what they're doing. Okay, but if we look here, right, we're looking at random variables. Okay, so again, it's the outcome that is of a random event. Okay, so some random event causes a numerical outcome. All right, now if we look at this thing called a discrete random variable. Okay, discrete random variable, it has a number of values that can be counted. All right, in other words, discrete random variables are include values that are integers. Okay, they include values that are integers. So typically whole numbers. All right, so some examples are the number of people randomly selected to be on a committee, lottery numbers, the number of motorcycles, the results after rolling a dice. Okay, so these can be discrete random values, right? And again, the difference here is it's still a numerical outcome of a random event, all right? But it is only certain values and it's usually whole numbers. Okay, so then if we look at probability distribution, all right, if we look at probability distribution, so again, finding the chance that something's going to happen. All right, so what we can do now is looking at our discrete random variable, we can find the chance that this is going to happen. All right, and sometimes probabilities are displayed in this thing called a probability distribution, right, or this table here. All right, and it's right down here as a good example where it shows the outcome and the probability. All right, so with this here, a couple things you need to notice is that it lists every outcome for whatever your situation is, and it lists the probability for each of those outcomes, even if it's the same for all of them. Okay, even if it's the same for all of them. So for rolling a dice, we can land on 1 through 6 1 out of 6 times. All right. And then when we're looking at this distribution here, it's said to be valid if there's these two things, right? This distribution at the bottom, the probability has to add up to 1, and all of the values have to be between 0 and 1, all right? Have to be between 0 and 1. Okay. Then if we want to look at our mean and our standard deviation, right? So we want to look at our mean and our standard deviation here. Remember, mean means our average, okay? Means our average, all right? So they give you a formula here that of course you can use. You don't have to memorize or anything like that, but they give you a formula here to calculate the mean or the average of our discrete random variable. Okay, so again, if we remember that this little e here means summation, right? So this is saying our sum of all of our values where you have the variable times by its probability, right? So x1 gets multiplied by p1, then that gets added to x2 times p2. Apologies, guys. I don't know why I keep losing you. It ends up to this mean summation here of u. Okay, and it looks complex, but it's really, really simple. Okay, you multiply each value by its density here. All right, so first question is this probability density valid? Okay, so we had 2 ways of checking it. All right, So we add them all up and it's equal to 1, and none of these values are outside of 0 and 1. Okay, so therefore it is going to be valid. All right, now if we look at what's our discrete random variable, okay, or sorry, the mean of that, okay, we use our formula here. Okay, we use our formula here. And what we do is we add, again, we add our probability multiplied by our outcome. So outcome probability plus outcome probability, outcome probability. Multiply those all out, add them together, and simplify, and we get our mean here. Okay, so again, basic algebraic skills here. All right, so this is our discrete random variable. This is its mean value. Okay, and the mean is also sometimes called this expected value. All right, and it's saying here, if you rolled the lopsided die many times, you'd expect the average of all the rolls to be 2.1. Okay, you'd expect it to be 2.1. Or if you look at this table up here, notice that our lopsided 4 dice, okay, the 2 highest values here are at 1 and 2. At 1 and 2. So it's more likely to land on those guys because of some factor, right? And luckily they told us it's a lopsided 4 die, right? So that's telling you the factor right there. Okay. Now, if we look and continue to look at variance and standard deviation of a discrete random variable. Okay, so now that we understand we have our mean, we can find our variance and our standard deviation. So remembering that variance is this value squared, right? Earlier it was s squared. This one is sigma, right? The s earlier was for sigma. This is the actual symbol, so it's sigma squared. And what we can do is follow this this equation here that should be a little bit familiar, right? We take our x value minus our mean value, we square that, and then we multiply it by our probability for that value. Okay, so looking at it here, start with our formula. Great. Okay, we'll substitute in the values. So of course, if we take a second to dissect this here, x1 is the value of 1. The average value was our 2.1, and it's multiplied by our probability for that first value. Okay, so that's that first whole thing. And if we look at the last one here, our x4 is 4 minus our average value, which is still 2.1. That whole quantity gets squared and multiplied by the probability for that fourth value. So multiplied by that 0.15. Okay. So noticing that is going to be important. All right. Then if we remember our difference between standard deviation and variance here, okay, all you had to do was take the square root of your variance. Okay, so they showed you the actual equation up here. All right, but remember what we found out was once we calculate the value for variance, all we have to do is take the square root of both sides, because again, variance is this sigma squared or that s squared, and standard deviation is just that s or sigma by itself. So you take the square root and we get our answer for our standard deviation. Okay, so then here's a couple examples that I'll let you guys go through on your own just for the sake of time since we're running out here. They're really good practice problems for you to be able to work through here. Okay, and then looking at this here, okay, of course, we talked about our types of data. We talked about our density curves. We talked about how to look at those discrete random variables and how to calculate those different properties there. Okay, so then here what we'll spend the last couple minutes talking about is looking at the different curves. All right, so what happened when we looked at the histogram with really large number of classes, right? It gave us that density curve, right? It smoothed out and gave us that density curve. All right, and most curves resulting from a probability distribution have this thing, and we call it a normal curve, all right? And it has these 4 characteristics, right? It's what's called bell-shaped. It has observations are near the mean of the data set. Okay, the observations trail off as you get away from the mean, and we have the mean, median, mode are all equal to each other, all right? And by observations, they mean frequency, right? So if we watch this video here, it'll explain. Okay, so this right here is called the bell curve, all right? It's called a bell curve. Okay, and you can see that it is clearly symmetric. And what it's saying by here, most observations are near the middle, right? This is the highest frequency in the middle of our graph here. And it gets lower as we go towards both ends. Okay, that U is our mean, right? It tapers out as we go. All right, and here's another example. All right, so looking at this here, all right, we can look, and our mean is also our median and our mode. All right, and there's a lot of different examples for that guy. All right, so if we look at the salary and the fish histogram, okay, so think of these normal curves as smooth shapes that model the histograms, okay? So clearly it goes right over the top and it models, but there's clearly gaps in the middle between the actual histogram and the bell curve, okay? And there becomes less and less gaps the more classes we have, all right? The more classes we have. And something that we want to point out here is that the normal curve is a model of the distribution and not the actual distribution itself, okay? So again, the normal curve, right, that black line up there is showing a model, right? It's showing a model, kind of a predicted thing. It's not the actual distribution itself, right? Because the actual distribution itself is all the individual values, right? It's all the individual values. So if we look a second here and we try to look at the area under our normal curve, okay, we look at our area under our normal curve. All right, we can see here both P and Q appear where it seems to change direction, right? And this is what we call inflection points. And if I pause this for a second here, remember, we were talking about up cup versus like a down frown, right? So right here, it looks like it's starting to form that up, right? Our concave up versus here where it's inflecting down. So that's that concave down there. Okay, so if we look here, this is exactly 1 standard deviation away from our mean. All right, so they took our mean and they added or subtracted our standard deviation value, and this is showing 1 standard deviation away. So if we fill in the area, we can see it's about 68% of the curve here. Okay, if we go 2 standard deviations away, we can see it covers about 95% of our area. All right, and then if we go 3 standard deviations away, it's covering, you know, like 99.7%, like almost the entire graph there. Okay, and this is going to be good here because it allows us to put actual values, right? Look at it empirically. All right, and all normal curves should have those characteristics. All right, so in order to check if a curve is normal, people use this rule here. So again, looking at that first standard deviation, it should be about 68%. Second standard deviation should be about 95%, and then our third standard deviation should be about that 99.7%. Okay, so looking at that rule, most data, 99.7%, will lie within 3 standard deviations of the mean, right? Should lie between 3 standard deviations of the mean. Here's an example that I'll let you get through on your own here to work through for the sake of time. But of course, again, the goal of that is to have all of the data within 3 standard deviations of the mean here. All right. Now, one of the problems with normal curves is that they don't always measure the same variables. Okay, so if we earned $3,000 and caught a salmon that weighed 17 pounds, do you have a good paycheck or a great paycheck? All right, do you have an average size salmon or a gigantic salmon? Okay, well, that's the question is within the population, how can you tell which one of these feats was more uncommon? All right, so what we can do here is actually look at this thing called a z-score. All right, and to point this out to you, what this is saying is that this is our data here. Okay, this is our data, and for example, it said 17-pound fish, which is about here. Okay, now the question becomes, is it a good or average size salmon, or is it above average? All right, and looking at this, okay, obviously 17's very far over here. So you would think that, okay, that looks like a gigantic salmon. But the questions become, you know, in this middle region here, okay, is it average or is it large, right? Or is it average or is it small, right? So it's really not in the far regions or the middle point here. It's when we have to guess somewhere in between. So this z-score here gives you a mathematical way of calculating it. So you're not trying to, you know, for lack of a better word, you're not trying to eyeball it here on this graph and make a judgment call. It's a mathematical score that tells you absolutely or not. All right, and so how you can calculate this here is you take your x value minus your mean value, and you divide it by your standard deviation. Okay, and then what this can do here is it tells you how many standard deviations an x value is away from the mean. All right, and if it's that 3 standard deviations away from the mean, that means you're at the really far edges of your graph there. Okay, so if we calculate this through here with our for a paycheck of $3,000, if our coworkers have a normal distribution with a mean of 2,700 and a standard deviation of 3,500, or sorry, 350, we start with our formula. Okay, we list our variables, we substitute in our values, and then we simplify. Okay, so if we look here, our z value is about 0.86. All right, and what this is saying is we're about 0.86 above our standard, or sorry, above our mean. Okay, so we're 0.86 standard deviations above our mean. All right, so what that means is we get paid slightly more than the average. We get paid slightly more than the average. Okay, so of course, you've got to understand your x values and how to look at your graph in order to calculate your mean and your standard deviation values in order to look at your z-score here, okay? In order to look at your z-score here, all right? But another way of looking at this is that it creates a standard value by which to judge things that may not be from similar populations. Okay, so for example, when we looked at our $3,000 paycheck, okay, versus our 17-pound salmon, okay, we were slightly above our average in pay, but we caught a gigantic fish because it was almost 2.5 standard deviations away. All right, so what we can do then again is we can actually look at our z-scores from a distribution standpoint, and we can graph them and make our density curve. Okay, so if we do that here, it changes the shape of the graph because now this becomes what we call a standard normal curve. All right, so again, it has characteristics to it. it still has this bell shape to it, right? It still has this bell shape like our fish example, but now instead of going from, you know, our low point of the fish to the high point of the fish, we're starting with our middle value being 0, right? Our middle value is 0, all right? Our standard deviation is 1, right? So we're going 1 standard deviation, all right? And finally here, instead of our x values here, instead of our x values being here, our horizontal axis is expressed as z-scores, right? So those scores we just calculated, right? We can put them on the x-axis here instead of whatever we were originally looking at. So no longer looking at paychecks or fish size, we can rearrange this in terms of our standard deviation here. Okay. And something that's nice about this here is that it has fixed percentages for all possible z-scores, right? It has a standard look about it. And we can look here at this thing called the standard normal table. And they have one here that's really good for you to maybe save and be able to use it. But it has standard normal table, right? So it's got z values, and it's got output values, right? And you can use that. And what they do here is they say, okay, if you want to know the area between 2 of these z factors, right? 2 of these z factors, you can look at the cross section. All right. So for the example here of 0.5 and 2.25, right? So looking here, they broke it up by, okay, 0.5, all right, sorry, 0.5 and 2.25, okay? So how you can read this specific one, which is different than this one here, we'll talk about that in a second. All right, what they do here is that look at the values. Okay, so this one here is going only to the 10th place. This one here is talking about the 100th place. Okay, this one's talking about the 100th place. All right, so if we look at this first value of 0.5, okay, we look at our z value, we go to 0.5. And since there's no value in the 100th place, we go to the 0 here. Okay, so this percentage for our 0.5 is this 0.6915. All right, but now if we look at 2.25, okay, we go down to 2.2 and we need to go across till we get to the 0.05 for our 100th place, right? So we do that cross section here and we're left with this 0.9878. All right, so we have both of these values now. And all we have to do then is subtract them. All right, all we have to do is subtract them. So we subtract the value of our left z-score from the value of our right z-score. Right, we subtract the value of our left from our right. Okay, because we're going to try to end up with, of course, a positive value because the area underneath our curve needs to be positive. All right, so that principle works for this as well. Okay, so again, it works for this as well, except for this guy here starts at negative values. All right, but this is still talking about your 100th place. So if we had 3.05, we would, or negative, let's go with negative 3.05. So I'd go down here to my negative 3.0, and I would then have to go over to my 100th place of 0.5. So I would come over and this would be my probability here. This would be my probability here. All right. So you can use this table for all values there under our standard normal curve. All right. And then the last thing that we'll touch on in this Zoom meeting here is looking at percentiles. Okay, so this one is going to be really applicable to you guys because of this is how they can look and say that you're in the whatever percentile when you take your ACT, or your testing scores were in the top whatever percentile here. Okay, so they use the statistics here and they use their standard normal tables to figure out how students compare amongst each other. All right, so they use that to compare amongst each other. All right, so we only got to about page 23 out of 30 due to, you know, a lot of tech errors, so I do apologize, guys. But today you're only covering 2 units. Okay, you're only covering 2 units. So we went over 4.3, you've got that one quiz here. And then we didn't quite finish 4.4, so you'll be responsible for finishing that up on your own and then doing the 2 quizzes, and if you'd like, the 1 extra credit journal opportunity. Okay, so again, I really apologize. If you guys have any questions about this unit as you're going through it, please don't hesitate to reach out. But you need to finish up. We ended on about page 23, so make sure you go back through this, finish this up, and take your 2 quizzes here. Okay. Other than that, guys, like I said, make sure you're trying to keep up with this work. It is the last week we have Zoom meetings, so work really hard so that way you have nothing you have to do next week. That's kind of my goal for you guys. All right, as always, if you got questions, reach out. Other than that, juniors, I'll see you at 10. Sophomores, I'll see you tomorrow. Bye, guys.